So thanks everybody for joining us today. Our presentation is on the effect of steel stud parameters on acoustical performance. I am Mike Raley, Director of Engineering with PAC International, and I have with me today Mr. Ben Shafer from PABCO, Gypsum, Quiet Rock. And what's your title, Ben? I can never remember. It's Director of Acoustical
It's
Sciences or something like that.
yeah. It's the Technical Services Manager of Acoustical Systems.
Of Acoustical Systems, chief acoustics nerd, right?
Yes,
Uh,
that's it.
yeah. So what we're gonna do today is, Ben and I are gonna kind of go through and just talk about steel studs and a lot of the things that he and I have learned. A lot of the stuff I've learned from Ben and all the testing that he and PABCO have done. So we're gonna talk about steel studs, steel stud parameters. Give Ben an opportunity to talk about all the awesome testing that he has done and what he's found from that. Just kind of have a discussion and then have some time at the end to open it up for folks for just more discussion about this. So with that being said, we'll go ahead and get into it. So I want to start off with this quote. I've been trying to figure out like how do I start this presentation? How do I get into all of this? And there's this YouTube engineer, I think this guy called Stuff Made Here, makes all kinds of cool robotic stuff and everything. And he, in one of his videos, he had this quote that's anyone can build a bridge, but only an engineer can build one that barely stands up. And it took me a second. I had to think about it for a while. And, at first listen, it maybe sounds like a dig at engineers. But when you think about it, you realize that building a bridge anyone would be sure will stand up means building a bridge that's way overbuilt, right? And that means lots of extra materials. In this day and age, we're desperately trying to reduce our material usage to reduce our impact on the world, on the planet. So overbuilding something to where there's no question that a bridge will stand seems a lot less appealing. And the engineer's approach of only using what's necessary seems much wiser, much more sustainable, much more efficient. But if you set out to build a bridge that will barely stand up, it means you need to be intimately familiar with all of the design parameters that affect its use, because any slight miscalculation spells the difference between a bridge that barely stands up and a bridge that never stood up at all. So when we specify walls that barely meet some minimum level of acoustical performance, we're also playing with that razor's edge of acceptability. Of course, a wall that fails acoustically, not the same sort of catastrophic failure as a bridge that fails, but noise is an environmental pollutant. It is a public health issue, and it's not something that should be taken lightly because over time, the stress that noise causes can accumulate and cause very serious health impacts for people and for the global population. So if we want to avoid building massive walls that we're sure will stop the noise, how do we make sure that our bridge will barely stand up? So we need to be intimately familiar with the design parameters that affects the wall's acoustical performance. And with steel studs in particular, there are a lot of different design parameters. There's a lot of differences in steel studs. And we need to know what those are in order to make sure we've got steel stud walls that perform acoustically. But a lot of times, we're not paying attention to all of those details. So today, Ben and I are going to kind of dig into all of that and start talking about some of those details. So, a story of like kind of why this matters. So when I was an acoustical consultant, we were working on a project that was a military base. It was all steel stud walls, steel framed walls. And early on in the design process in SD, we gave them different wall options. And at the time, this was before Ben had done all of his testing, so we didn't have that to go to as a resource. So we went to the National Research Council of Canada. They've got a big compendium of a bunch of acoustical tests, and we went there. And so we looked at different steel studs in there, right? They've got 25 gauge steel studs with the gypsum board attached directly. Single layer of 5/8 type X on each side, STC 59, kind of around that STC 50 threshold we see a lot. But we weren't sure if they were going to use 25 gauge steel studs. So we also gave them options for 20 gauge steel studs. And with 20 gauge, they had to use resilient channel because the 20 gauge steel was stiffer. We see that without resilient channel, it doesn't perform as well in this data. So we said use resilient channel. You also hit that STC 49 target. But so we gave them these two options. because at that point in the design process, they hadn't figured out what steel studs they were going to use, right? It was still kind of up in the air. So like, here's your options. Project moves along, we make more recommendations, go through plan checks and all of this, and eventually one of my coworkers went out to the job site to do a site walk. Everything was framed. I don't remember what he was there to kind of inspect, but all of the steel walls were framed, but none of the drywall was on. And so he was looking at the walls and he was like, oh, what wall design are you using? You guys, it looks like you haven't put the resilient channel on. Like, I thought you guys were using the heavier gauge studs. And they're like, oh, no, we're not using resilient channel. And he's like, well, wait, what like gauge studs are you using? I'm like, oh, these are heavy gauge. They're 20 gauge or heavier. He's like, well, you have to have resilient channel. They had missed the two wall assemblies, and that they needed, if they went with the heavier gauge studs, they needed to use the resilient channel. And it wouldn't have been that big a deal to just add the resilient channel. It would have been an unaccounted for cost and, in terms of material and labor. But the real sticking point was that at that point where he was on site and caught it, all of the door frames had already been put in place. And so they were sized for the walls with no resilient channel. Of course, the resilient channel creates another 1/2 inch offset that they had to accommodate with all of their door frames, figure out how to get that gypsum board to tie into the door frames. So that was a huge thing on this big military base. Just this one little detail that was missed that caused a lot of headaches on this project. So perfect example of why this is really important and how it can cause issues for you. So what they wound up with was something like this. And this is from the test data that Ben and PABCO have done from their sound design guide. So as an STC 41 for those 20 gauge, 33 mil steel studs. And we'll talk a little bit about mil thickness and all of that. So Ben, maybe you can kind of join me in talking about this.
Yeah.
Just the basic parts of the steel stud and kind of what matters and things like that. So we've got a little diagram at the top, right? Just to make sure we all got the right terminology. So the web is really the depth of the stud, right? So this is a cross section like you're looking down on the stud. And then the flange is the part that the gypsum board gets attached to. And then there's the lip, which is just like the little return on the end. So those are the kind of basic dimensions of the stud. And then you have the gauge or the mil thickness. And Ben is really the one that has pushed me to start thinking more in terms of mil thickness rather than gauge. But it's not just Ben, like it was AISI, right, Ben, that moved from gauge to mil thickness.
Yeah. So AISI did that long before we even started. Well, not long before, but a few years before we even started exploring steel stud variation for a sound isolation. And they had different reasons for that, but it matters a lot acoustically as well. And then there's other, there's the stud. So you'll have the difference between, the flange, lip, web, these are all properties that are specified in AISI specifications for standard steel. But then if you use EQ steel, there's a whole different other AISI standard for EQ steel that actually isn't as rigidly specified in terms of flange, lip, and web and all that, because EQ steel is meant to have different shapes and stuff and still achieve the same structural load requirements.
So for those that aren't familiar,
weird.
Yeah, right. That can make it weird. So for those that aren't familiar as much maybe with the EQ studs, what are EQ studs?
So equivalent gauge, well, EQ. So Clark Dietrich in early 2000s, they patented. It came out with a new design of a steel stud that used thinner steel but had equivalent structural properties to the standard steel stud. And so they reduced the mil thickness, changed the design of the stud, and were able to achieve similar structural load requirements. And so, that's what the EQ, it's the equivalent gauge. So even though the stud is maybe thinner in steel, it has an equivalent gauge of a 20 gauge or whatever, because it still meets the structural load requirements.
Right. And so it's because of, the EQ studs and all of the variation in steel thickness and things like that. I mean, that's one of the reasons, I guess, but that's one of the reasons that we've moved to talking about mill thickness, because in part what we care about is the actual thickness of the steel.
Right.
Right.
Acoustically.
Acoustically, yes. I found these. So these are from an ASA presentation that Ben did from San Diego, I think in 2019. And this is where he presented a lot of this data. And as I was going through this presentation, it's something that I've been shared with me and I've referred back to a lot. I thought this was really interesting. So this is kind of the EQ studs, and I guess standard 30 mil and 33 mil, like 20 gauge studs. But this is where they were. So in 2018, one thing I thought was really interesting is this Pro Stud 20, the Dietrich Pro Stud 20. So in 2018, it was using 20 mil steel. In 2019, it was 19 mil, and now in 2023, it's 18 mil. So they have continued to decrease the thickness of the steel, but still maintain that strength through just changes in the shape or whatever, different engineering and stuff like that. So again, trying to build a bridge that barely stands up, right? Trying to take as much material out of it as possible. So it's interesting to see that these things have changed significantly even over the course of just 5 years. And so you see that there's a whole bunch of different ones. So it can be hard to keep track of. And so it's important to just pay attention to the details of the steel studs that you're working with on a project. Ben, do you have anything to kind of add to this?
No, I mean, no, it kind of speaks for itself, really.
Yeah, there's just so much. So so really where this comes into play, and Ben and I got into this a lot with some testing that we did for a big cinema project where they were going to have these walls that might go as high as 60 feet, 20 meters or something like that. So we were trying to figure out what kind of studs could actually get there. So one of the things that I've learned about as I've got into this is the wall height limitations, right? And that's one of the things that can force you, even if you've got non-load bearing steel framed walls, can force you to go to heavier gauge studs, just because those thin metal studs just can't go that high. They're too flexible. So the SSMA, the Steel Stud Manufacturers Association, has these wall height tables. And one interesting thing in here is they have different ones. So they have it for composite, fully braced, and braced at 48 inches on center. The composite tables assume, and you can see it in the quote here, the text, that they're based on a single layer of 5/8 gyp installed in the vertical orientation to both sides of the wall over the full height of the wall. So they're using the gypsum board to control those flanges of the steel studs so that they don't twist, right? Because if they're in that straight up and down orientation, that's when they're the strongest. And if they twist, it can weaken them. They can't carry as much load. They're not as stiff, whatever. So you use the gypsum board to control those flanges, make sure it doesn't twist, get out of alignment. But for acoustically rated walls, we're often detaching the gypsum board on at least one side of the wall to provide acoustic isolation. So if you're using resilient channel or sound isolation clips or any of those kinds of things, you no longer qualify as a composite wall. So here I just took a 3 5/8, an 18 mil, so a traditional 25 gauge steel stud, 24 inches on center, and the limiting height was 13 feet 2 inches. But if I go to the braced at 48 inches on center, that wall now goes down to 9 foot 3 inches. So you might run into situations where you think that maybe acoustically you can use a 25 gauge or an 18 mil steel stud to get that acoustical performance. But if you're needing to do extra things to it or whatever to improve its performance or whatever, you might have to go down in stud gauge in order to get to the wall height. So there's a lot of sort of nuances in here that can change the stud gauge you need for a project and can affect your acoustical performance. And that's, I think, one of the things that we ran into on that military base project is they had some very tall walls, and so they had to go to heavier gauge studs. Ben, what are your thoughts on these, kind of what gets you thinking about stud gauge? What kind of things do you look out for with stud heights and when you're selecting studs for acoustical tests and things like that?
Right. No, this has come up, and we actually have done testing with different kinds of bracing in the lab. I mean, we can't test walls that are super high in the lab, but you know, we can brace it at mid height and see what happens. But yeah, no. So all this stuff. I mean, what this results in, and like you were saying before at the beginning, unfortunately what it results in is it results in a lot of stuff that you have to take into account. Yeah, a lot of stuff you have to think about when you're designing a steel stud partition for specifically for sound isolation, because you might need and yield strength. The yield strength. You might have 3 different companies who sell an 18 mil steel stud that works for your project for the load that you need and the limiting heights, but then all those 18 mil studs have different yield strengths, which means they use different strength of steel for the cold rolled channel, and that will affect performance too. So like it's just a lot. There's a lot of variables. So it's important to be, just like they were saying, the engineering. You know, it's important to address it. Not in a brute force, like I'm just gonna like assume, like they used to just old if you look at old sound test reports, they used to just say steel studs, you know.
Yeah.
And like we just can't do that anymore.
Yeah, and that was actually something I meant to put in here, but I forgot. I had gone to pull out you know, some of the acoustical test, you know, resources, right? So if you're working with steel stud assemblies, right, and you're trying to figure out the acoustical performance of them. So I showed the NRC test report, and that did look at the specific gauge of the steel studs that were in there. So it gave gauge, not mill thickness, but that was, you know, done in the 90s. That was before the industry had moved to mill thickness. So they gave you that information. But there's a lot of other resources that I know a lot of acousticians and architects go to that don't give you that information necessarily. So one example would be the California book, or the
Yeah.
big, which is a book of acoustical test data that the state of California put out. I don't know, was that back in like the 70s, Ben? Like
68 or 69, I think. Yeah.
Okay, late 60s.
70s.
So it's this compendium of a bunch of acoustical tests from the time. But in there, for their steel stud walls, it just says metal studs.
Yeah.
It doesn't even specify the type of metal, let alone like gauge, thickness, any of that kind of stuff. It doesn't give you any information about it. So, and there's not really any notes in there that I'm aware of that sort of say, unless it's noted, these are this gauge or something like that.
Right.
The Gypsum Association.
Even I was
yeah.
going to comment on that. Yeah.
Yeah, go ahead. Talk about that one, since
even
you're
the
intimately
Gypsum
familiar with it.
Yeah, even the Gypsum Association. But previously, not now, but previously in the Gypsum Association manual, there was a note at the beginning saying, you know, unless otherwise specified, studs are 25 gauge steel. You know, and it didn't even mention. Also didn't mention mill thickness, and then I got hired with PABCO, and we changed that. But now, so I love the story that's, you know, that industries even can change. You know, somebody comes and says, hey, there's more new information, and there's more to this than you guys are, you know, putting in your manual. And they're like, okay, well, let's change it then, and we have. So I think that's a good thing. But also, it's important to note historically that, like, yeah, you might not get an old test report that you'll have any confidence in terms of like knowing what that was actually tested, you know, in terms of steel mill thickness and gauge. So it's less reliable on older tests.
And Ben, when did that transition in the GA manual happen, where they started on each individual test actually listing the mill thickness?
I think the 2015 or 2018 GA manual.
Okay, so for any of those of you out there that are using an older version of the GA manual, make sure you get a new version, because it has a lot of good information. And really, like, and Ben and I have talked about this a lot with other things too, for making sure that the acoustically tested assembly completely matches the requirements of the fire design in terms of, you know, stud spacing, gypsum board thickness, gypsum board attachment, the screw spacing, all of those kinds of things. The Gypsum Association, and Ben in particular, has done a lot of work to clean all of that up. So it is a much better resource now, and you will see in all of the steel stud assemblies the mill thickness of the studs listed in there. So that's a great great resource, and good to know that it's been updated. You know, maybe set aside those older versions. And Ben, I see in the comments that Steve Pettyjohn says the California book was published in 1980.
Oh, 80. I thought it was earlier than that. Wow. Okay. Well.
Yeah. So, and I see Steve also had a good question about how does the EQ stud affect fire rating? And I think the sort of simple answer of that is it becomes a proprietary product, and so then you have to look for it specifically referenced in a UL design rather than generically referenced just in terms of like stud gauge or mill thickness. Is that correct?
I think that's correct, but I think also there might be a different designation in UL for EQ studs too. It might, like, you know how like CKNX .CKNX is like gypsum type X, you know, in the manual. So like there might be a different designation for it, but usually I think you're right. It's listed as like one of the option B, C, D, or E or whatever. Like, but so, and I think that most EQ studs have equivalency in fire as well. Because when I've looked at like U425 or V4, 464, you'll see like the general listings, but then you'll also see some of these EQ stud listings as well in the same design. So I think that the steel industry had that in mind as well, in addition to structural load, but I don't know if that's equivalent for all companies and products.
Yeah. Mike or somebody else, if one of you could allow Don Allen to turn on his mic, he might be able to jump in and then contribute to these as well. So all right, so I'm going to move on to the next slide. So we talked about those are braced at 48 inches on center, and this is a perfect time to make sure Don can turn his mic on. So there's different options for bracing. And so when Ben talked about like, hey, we've done some testing with bracing in the lab, these are the different options for bracing that those SSMA tables refer to. So A is a cold rolled channel that goes through the knockouts in the studs. And then there's like little clips, there's, you know, sort of generic pieces, or there are proprietary clips and systems that you can use in there. But that's used to help stiffen the studs. The other thing is you can just attach a piece of metal on the side to the flange of the studs, screw it to that. You also have to do blocking at the ends. So you're adding all of this extra stuff in there that's stiffening it and sort of affecting the wall. So when you look at bracing, this is what they're talking about in those tables. Ben, without, you know, in the interest of time, without going into too much details, like, do you have any other sort of just like general comments on bracing and acoustics?
Yeah, I mean, I don't want to get into too much detail, but I was surprised at how little, it's not like it didn't affect things at all, but I was surprised at how little bracing affected the sound transmission loss in the lab. I thought it would affect it a lot, especially for like an 18 mil steel stud. And it does affect things. It just doesn't affect it like I thought it would.
Yeah, right. So if you're doing like load bearing steel construction, and I've seen an uptick in that, as you know, I think with lumber prices when they went through the roof, I've heard that some projects moved to steel. I also know that steel stud construction is being used some in like hybrid mass timber construction, where they're doing mass timber panels, but then they're doing steel framed load bearing walls. So even in mass timber, it's, you know, you're getting these. So in those sort of load-bearing things, your stud thickness, the strength requirements for your studs are going to vary from floor to floor, right? So your lowest floor that's carrying all that load is going to need much stronger studs than the top floor. So how do you determine and specify the acoustical performance of those walls, what kind of happens as you move up or down that building and you change your stud thickness? And are those things really being accounted for? So this is where we're going to kind of get into Ben's data, because Ben's done a lot of great testing. And again, in the interest of time, we'll not spend too much on this. I've got a lot of extra slides in here for you, Ben, too.
Okay.
Yeah, so this is Ben's ASA presentation from 2019 in San Diego. So I'll kind of let you introduce it and kind of just take it and do a quick run through some of this, Ben, and I'll ask you questions too.
Yeah, we don't need to, and we already did a lot of this intro stuff, so you can kind of just skip. We did a lot of tests. That's kind of what that's saying.
Yeah,
we did a lot. When I
tests.
say a lot of tests, I mean like 3 times as many tests as NRC did.
Yeah, you did a ton, which is why this is such a great resource and why I wanted to highlight it again, because it really is a good resource.
Yeah, so what we did, so this is a good slide to show. So what we did was we tested single, and we've done more since then for steel width and other things, but we did single 3 5/8 inch 90 millimeter steel studs, 16 and 24 inches on center, with and all of them had the same R13 fiberglass 3.5 inch bat in the cavity. And then we did several configurations with like single layer Type X gypsum wallboard, double layer, single layer with RC, and then damped panel on both sides, the Quiet Rock damped panel. And then and we have the screw spacing remained the same for all the tests. And the RC was spaced 24 OC. And the RC was, it wasn't RC, it was RC Deluxe, which is an exception to the rule.
Yeah, right.
Like,
so
we did all that RC testing too.
Yeah, and there's many folks on here who know that conversation, but for those who don't, like, most acoustical testing is done with RC Deluxe, which is the dog bone shaped knockouts in the web. And that tends to perform significantly better than a lot of the other RC types. So that's another thing to look out for. And if you've got questions about that, Ben and I will have a lot to say about it. But that's a discussion for another time. So these are the wall types. And so then here's some of the data. So kind of tell us generally what this is showing, what you found from this, Ben.
Oh yeah. So I mean, this is just a 16-inch on center steel, and then you can see on the bottom, you can see that 97 mil is 12 gauge, so that's the heaviest we did. And then we went from 97 mil to 68 mil 14 gauge to 54 mil to 43 mil on down to 15 mil EQ. And when you look at just the STC rating, which doesn't tell you, I mean, well, yeah, it didn't tell. Anyway, so yeah, the STC rating, I have opinions about that anyway, but we don't need to talk about that here. But if you look at just the STC rating, you know, for as you go across the steel stud mill thicknesses, when you have Type X on the wall, you get this like it's all the same until you get to 33 mil, and then it jumps, and then it kind of stays the same. And then with double layer Type X, it varies more between the heavier gauge steel studs, but there is again a pretty big jump when you get to the 33 mil studs, and then an even bigger jump when you get to the 15 mil. And then when you have RC on the wall, there's less variation between the stud mill thicknesses, but you still get a jump when you go to 33 mil. And then with the damped panel, it's performed like a little slightly better than the double X on each side, and usually, and then it also jumped around, and then 33. Ironically, for the damped panel, 20 mil 20 gauge EQ was where it like had a more significant increase.
So it's just it's complicated. All these different parameters like affect it differently, right? Which is why, you know, trying to estimate what an assembly is going to be, or trying to figure out all of this stuff without a lot of data to go on is really difficult.
Right.
And then when we move to the 24-inch on center stud spacing, you'll notice that
everything changes.
These are the same scale, so you can see that everything goes up in performance.
Right.
And yeah, things change significantly.
Yeah, the trends are different. Like it's just there's more variation with the single layer Type X on the heavier gauge studs. and it just kind of goes up gradually from 54 mil, you know, and then and it was just really interesting. And 54 mil was the least performing mil thickness, not 97 mil, which I thought was interesting. There was something going on with the 97 mil and the 240C. Anyway, so it was that was really interesting too. And then the damped panel looked a little bit more like the RC in this case, where it didn't really matter as much what the steel mil thickness was. It performed pretty similarly.
Yeah, there's only a 2-point difference in the STC ratings with the damped panels, which is like very, very consistent.
24C, yeah. So that was interesting too. Yeah.
Yeah. So there's, you know, different things that you can play around with. And I know in talking to some drywall contractors, like estimators for drywall companies, they've said that they tend to try to use 24-inch on-center stud spacing and just increase the mil thickness of the studs to get their wall heights that they need, because the labor of installing additional studs is more money than the little bit thicker steel studs. But if you're sticking with 24 inches on center, there's also maybe this added benefit that you get better acoustical performance, and at least with the damp panels, less variation in your acoustical performance too. Yeah. So, you know, so in looking at this, if you're thinking about some big stacked load-bearing steel stud building, you're not just looking at the acoustical performance of the wall with one type of stud, but with all of these different studs. So in order to make sure that you're getting a consistent acoustical performance throughout that building, trying to come up with systems that have less variability with stud gauge could be a good design tactic. So here, maybe using, you know, 24-inch on center spacing instead of 16 could be a way that you could better ensure more consistent acoustical performance. So then here's the difference between the 24 and the 16 inches on center, right? So this is how much better the 24-inch on center was than the 16, right?
Right. So for like RC, you look at the RC Deluxe, there wasn't a big difference. A big difference and the difference for almost all the solutions, the difference got smaller as you went lighter in gauge. The difference between 24 and 16, which is what we've seen in the past. But yeah, it differed depending on the solution you're providing. If you're doing multiple layers of drywall versus a single layer drywall, if you're doing damped panels versus RC versus whatever, you know, the difference between the 24 and 16 was interesting.
Yeah, and you know, one thing that I kind of I saw here that stuck out to me was that the resilient channel seemed to reduce and kind of minimize the effect of the stud spacing. So by limiting those connection points, you limit those connection points to the studs, you limit that effect, and the studs no longer are controlling as much how the gypsum board responds. Right. So Neil Shaw, to get to your question about TL data versus frequency. So here we go. So there's a ton in here, and so there are a lot to look at. So you'll see that on the vertical axis you have the mil thickness going from the thinnest at the top to the thickest at the bottom, and then on the x-axis, the horizontal axis, we have frequency. And then the colors indicate the change from 24 inches on center to 16 inches on center. So it's how much higher the TL was for 24 inches on center versus 16 inches on center. Is that right?
Or Ben? Lower. Yeah, or lower. See,
or lower. Yes.
This is what I found interesting. If you look, I mean, it's hard to interpret this is really nerdy. So for those of you who don't really care as much about this aspect, it's going to be boring. But so what we're doing is we're taking all the frequency content and the sound transmission loss, and subtracting the 16OC from the 24OC, and looking at the difference. So if at 125 hertz, right at 125 hertz, there's a pretty big increase for 24OC versus 16OC. If your studs are at 24OC, there's this big boost that happens at 125 hertz. But at 80 hertz, there's a pretty big decrease. Not as big as the increase at 125, but it's pretty significant for, say, heavier gauge steel, 43, 54 mil, 97 mil. So, and what that means is, like, if you really care about 80 hertz, it might actually not necessarily be more advantageous to go with 24OC. spacing. Same thing if you look at 2K, like the higher frequencies, you drop in performance, especially at 54 mil. You get performance decreases for 24OC versus 16OC, which we were, as we did this research, I was really fascinated with this data, but then also like, what? So wait,
why?
They're like, everybody's like, yeah, go 24OC, and then they're like, yeah, you're going to get this pretty big, like significant increase at 125 hertz, but kind of everywhere else, it kind of doesn't matter, or you do worse.
Yeah, and the compounding factor for this is, for those of you who don't spend a lot of time looking at SDC test reports and all of these kinds of things. So the frequency range that we look at for an SDC rating that's used for the SDC calculation is from 125 hertz to 4,000 hertz. So what's happening at 180, 63, 50, that's completely ignored in the SDC rating. So, and oftentimes with walls, because of the way we do the calculations, this 8 dB rule, which I've got another presentation on that, the transmission loss at 125 hertz often winds up being what dictates the SDC rating for the wall. It controls the SDC rating. So this big change at 125 hertz is why we might be seeing big changes in the SDC ratings between 16 and 24 inches on center spacing. But there's other stuff happening at these other frequencies, and oftentimes it's going in the opposite direction, which was really fascinating for me when Ben first showed these to me. So here's the same thing, but for 2 layers of gyp on both sides. So it's similar sort of trends, right? But even more pronounced.
Right.
Like
more
for the 97 mil, we're 20 to 23 dB difference.
Just at 125.
Yeah. But over here, you're actually worse.
Yep, and below.
Yeah. Yeah, and below.
This is Don. I got to step in here and say something if you can hear me.
Yeah, we can hear you, Don.
I'm background structural engineer, and a decade or so ago, I was technical director of SSMA, so I recognize all the stud manufacturers' numbers and catalog data. But I'm thinking about now. I'm with AWCI, the walls and ceilings contractors. I'm thinking about all the contractors, estimators, and architects that are on the Zoom meeting today, and they're thinking, okay, well, I attended this thing that Mike put on, or some other acoustical presentation a while ago. There are all these rules of thumb, but this just threw a lot of that out the window. So what I've told what I've told people, and this is cool stuff, being a nerdy engineer myself, it's cool seeing it. But I tell architects, I say, do a performance specification. Say, okay, say what your STC has to be, say what your loads have to be, say what your pressure has to be. Be careful using the G word, gauge, because it means different things to different people. And then that let them meet the performance that you want. And then my poor contractor members come back and say, well, yeah, but look at all these things I've got to figure out to meet these architects' performance. That's what I'm hoping we can clarify for some people today.
Yeah, and that is the trick, right? Is there's all of these details. And so the first thing I will say is hire an acoustician. There's a lot of them on this call. Hire an acoustician. If you're working on those projects, the National Council of Acoustical Consultants has a directory of acousticians. You can also go to INS, the Institute of Noise Control Engineers. There's a membership directory on there. You can look for people that are members and also those that have been board certified, which is, analogous to having your professional engineering license. It's a big long exam and things like that you have to go through. So go there to look out for those resources, because those people are the ones that are, asking the questions in here about the frequency data and really digging into a lot of this stuff. But then also, you can reach out to manufacturers. This is why Ben has done all of this, is to help answer those questions. And PABCO has their sound design guide, which has a lot of this data. And I think they also have a like an assembly selector kind of on their website where you can go look at, acoustical performance with different stud thicknesses and that kind of information. PAC has our online assembly selector where you can go get test results and things like that. And so one of the things is, like, there's all this variability in here. So how can we reduce this variability so you're not having to pay attention to all those details? And that sort of brings us to this next slide. Well, here's the one with RC.
Sorry, I wanted one other thing to note, Mike. I was going to say, I was just going to say, that's my first question. Every time I get a an inquiry from a customer or a client or acoustical, I'm for a project, my first question is, do you have a consultant on the project, and who is it? You know, so you can interface with them. And I just think that is, I can't stress enough how important that is.
Yeah,
How often
that's my
is
question
the answer
too.
to that question yes?
No, not often enough.
Okay,
not often enough.
That's what I figured.
Yeah. Not often enough. And I think with steel framing especially, there's a lot of like delegated design, like what you're talking about, Don, where it's a performance specification, but then it's left up to the contractor to actually figure out how to meet that specification.
Right.
Which
And
obviously, as you see here,
they delegate their design to structural engineers, who I will admit know very little about acoustics. They know some of these rule of thumbs that you just blew out of the water. So be careful.
Well, and I will be quick to admit that I know nothing about structural engineering. So that's why I'm happy you're here, Don. So, so the next one I wanted to go to is the test with resilient channel, because if you look at the difference between these two, it's just in terms of the colors, without really digging into the details, the difference is pretty incredible. So Ben, what did you get from this one?
Well, what we found, like, even so you saw this sort of in the STC charts, but then if you look further and you look at all the frequency content, you're like, wait a second. So it's only at really specific frequencies that the different gauges affect the RC. But for the most part, that blue, it's mostly blue, which is -1 to 2 dB. So which is not statistically significant at most frequencies. So it's so you're not generally seeing a very big difference between, when you have RC Deluxe specifically, you're not seeing a very big difference between 24 and 16OC. So again, like you were saying before, how I conceptualize that is that the sound energy that's radiating through the structure, through the wall, is I get that the studs themselves are having less, they're dominating less of that energy. They're no longer, the studs are no longer the dominant path for sound transmission through that wall.
You're getting more transmission through the airborne path, which is not as much affected by this.
The cavity, the mass, all that stuff. And that was all the same in these tests.
And also by changing stud spacing and stiffness, you're also affecting the radiation efficiency of the gypsum board.
Right.
Whereas with the resilient channel, the resilient channel is the same stiffness, it's the same spacing. So, the radiation efficiency of the gypsum board on that side of the wall is much more similar, more consistent. So this just, using some sort of method to decouple the gypsum board from the studs, reduces the variability with stud spacing and gauge, seems to be. So, and then the last one, here's the constrained layer damped panels. Here's quiet rock.
Right.
And you see, go ahead, Ben.
Yeah, I was gonna say it looks similar to the double layer in terms of the difference between 24 and 16OC. You get like a large improvement overall for the stud wall, but like again, you go to the coincidence you just go to that region at 2.5K, and you're getting 4 to 7 dB lower performance when you switch to 24OC, even though the STC rating looks great, like we showed before. Like, whoa, those STC ratings are way higher, on 24OC for the damped panels. But if you care a lot about speech privacy, then you might want to take a look at that 2.5 kilohertz drop, or what the average TL is for the, because that's how you calculate speech privacy. But like, it matters, like, and 125 hertz is maybe a little bit, it's still important, but it's a little less important for, like, say, speech privacy than it is for like a home theater or something like, something where you have a lot more low frequency content. You just have to, again, not to be a broken record, you need to hire someone who's going to look at this stuff and then say, oh wait, I know what kind of noise we're trying to deal with, and and we'll choose the best design for that, based on the data.
Yep. Exactly. Yeah, as I say, single number ratings don't tell the whole story, and this is pretty clear evidence of that. So these were your sort of conclusions from the slide. So STC calculation rating, there's some misconceptions about actual STL performance, and I think you had gone into some other things in your presentation with like mass air,
Yeah.
mass resonance and stuff that we
Right.
won't get into here. But this next point is what we've been talking about. For many 1/3 octave bands, the many frequencies, the 24 inches on center actually isn't necessarily better than 16 inches on center, which is the common assumption, right? And that a lot of these things are really controlled by the transmission loss at 125 hertz,
Right.
which is, so just pay attention to the details. So what all of this has got me thinking is, okay, so if the resilient channel reduced the effect of stud gauge and spacing, what would happen with clips? So I want to investigate that, because if the resilient channel, reduces the effect of the stiffness of the studs and all of that, then clips and hat channel, using the RISC 1 and hat channel, should probably do even more of that. Because the thing with resilient channel is, if you change the stud spacing, you are changing the number of connection points, because the resilient channel is connected to each stud. But with the RISC clip and hat channel, the spacing of the clips and the hat channel stays the same regardless of the stud spacing. Now, there may be some exceptions to that with, fire rated designs and things like that. But generally speaking, your clips on a wall are at 24 by 48 inches on center, sort of regardless of what the stud spacing is. So you're even further reducing that variability. So here's a test plan that we are hoping to go do. And I'm working with Ben to sort of coordinate this. And so all of the testing that Ben had done, he had done at North Orbit Acoustical Labs. We're going to do all of this at North Orbit Acoustical Labs too. There's some time in between them, but we're trying to sort of control as many variables as possible so that this can be some additional data to go on to what Ben has already done. And we're not going to go do all of the different permutations, but we're looking at sort of the typical, a 33 mil and also a 54 mil, because that tends to be the worst performing in Ben's data. And we'll at least look at that and see, and we'll do some tests with a single layer each side, 2 layers each side. And we're also going to do some tests with backers to see how adding a acoustically isolated backer, RISC backer, to isolate cabinets, grab bars, medical equipment, any of that kind of stuff, how adding that in there affects the performance of the wall. So we're doing this, and we'll hopefully do this the first month or two of next year. Perfect time to be in Minneapolis for some testing. It's January and February. So thanks everybody. We've got a few minutes left, and I am happy to stay on past. I don't know how much time Ben has. I see
can stay on a bit past too.
A lot of comments. I see a lot from Norrell Stewart, Neil Shaw, Steve Rittmuller. There's a lot of good comments in here. I think we can probably go and maybe allow everybody to turn their mics on if anybody wants to jump in. So I'm gonna allow mics. Please don't everybody unmute, because it'll just be chaos. But if anyone wants to jump in, that would be awesome. So
hey, but before you do everybody's mic, since mine's already open, I'm going to go ahead and ask one. And
yeah,
this
sure, go
this
for
was
it,
a
Don.
comment that this is Don. There was a comment in the I think it was the chat, and that somebody had specified a 2-inch flange, and then the contractor or whoever had supplied 1 5/8 inch, and they were running all sorts of issues. One thing I didn't see as a variable was flange width. And have either of you found that makes a difference?
No, I haven't tested flange width yet.
Okay, and it probably doesn't, but just wondering, because one of the things that we run into as structural engineers is we're going really tall. We can vary the flange width, we can vary the thickness, and we can vary the spacing. And if flange width doesn't have much of an effect on acoustics, then that might be a better idea for us as structural engineers because we can go up to 3.5-inch flanges on these things, depending on what manufacturer you've got. So that might be a better way to keep the thickness down and the spacing up.
That's really interesting, Don. I really appreciate you bringing that up. Actually, I've never thought of that. I did do I did do. I've done some like theoretical prediction stuff, and not to get too nerdy, but like I did a moment of inertia calculation for a C-shaped steel stud, and which includes the flange width, and that does affect the acoustic impedance of the stud, which basically says it affects how the stud behaves when it interacts with an acoustic wave. And so it might affect the acoustic performance, but I'm not sure it will affect it enough that the laboratory instrument would be able to pick it up. I don't know though.
Ben, I see Norrell's got a hand raised and his mic unmuted.
Oh yeah, go for it, Norrell.
Yeah, it's not about the flange or anything. I was just going to speak about this 24 versus 16 and this weakness at either 125 or 80 hertz. That's well known to be a stiffness resonance effect,
right?
Which, when you have direct attached to gypsum, is actually stronger than the mass air mass resonance effect, which we often many years ago assumed it to be.
Right.
But it occurs at 125 to 160 hertz when you have 16-inch on centers, and it drops down below 100 hertz to say 80 hertz when you have 24-inch on center. So that's why you see that shift and so forth. And it is essentially eliminated when you go to resilient channel. You don't have the stiffness anymore. Okay. And so that's why it doesn't show up. And it's less effect when you have a 25 gauge. You'd be interested in looking at your test data on that. But it should show up somewhat less effect on 25 gauge studs than say on a very heavy gauge stud. But it may still be there, and so forth. And the other thing, of course.
Yeah, there you go, Mike. we did look at that.
Okay, let me say just one other thing. Of course, when you just do a single test of each design, we all know you got test-to-test variation, and that introduces some of the inconsistencies that you see. And of course, if you had the budget to test 5 samples of every design and average them, you could probably eliminate some of that inconsistency that seemed to be illogical in some of the results.
Well,
maybe not all of it, but some of it.
Well, to that point, Norrell, that's why we used the same exact lab and the same even make, model, and testing materials.
Yes, but even with that, I think you could get different results test to test.
Correct. Yeah, you're not wrong. You're not wrong, but yeah, so that we tried to eliminate as much of that variable as we could.
Understand.
Yeah. So if you
what
see,
you got here, Ben?
a 1 or 2 point variation. Yes. Okay. I was just gonna say, if you see it, for those of you, looking at this, not as familiar with, the test variation and things like that Norrell's talking about, if you see a 1 or 2 point variation in these things, that's probably not meaningful. You could just redo the test and see some variation like that. But if you start seeing, those ones where we see 5, 7, 20 dB, like those are significant, and you're gonna see those, rank order the same way from test to test.
We'll just say that sometimes if you only got a single test, on rare occasion, it's possible to have a 4 or 5 point error off from things.
4 or 5 dB, yeah.
Most likely,
especially at lower frequencies.
Most likely, as you say, it will be a 2 dB, but it can be greater.
Yes, right. Yeah, and especially at low frequencies, right, Norrell?
Yeah, depending on the frequency range you're looking at.
Okay, go ahead. What do we got on 25 gauge versus other gauges on the 16 versus?
And Norrell, I got to ask, when you say 25 gauge, what thickness do you mean?
Well, I understand. I'm meaning one of the thinner gauge.
Yeah. Okay.
Okay.
And speaking of 25 gauge, so I'm currently working with Evelyn Way of Maxon on running a round robin for ASTM E90, which is the SEC test. And we're doing it on walls, and we're doing it on steel stud walls. And Clark Dietrich is providing the studs for us. And they're manufacturing them for us for this, so we can make sure that we get all the same studs and everything like that. And they're cutting them to length, and we're sending them out to all the different labs that are participating. And I said, wanting to kind of stick with traditional stuff, but there's a lot of data for out there. I wanted an 18 mil, 25 gauge, 33 KSI, 3 5/8 steel stud. Dietrich came back to me like, yeah, we don't make that. That's a special order item. We've got these 15 mil 25 gauge EQ stud that you can use. But it wouldn't hit the span heights for it weren't enough to get to the wall height for one of the biggest labs that now has a much taller opening. So we're having to go to a 20 gauge EQ, which is, I think now they're 18 mil Pro Stud 20. So
most of the 20 EQ studs are the old 25 gauge thickness. And I saw somebody in the chat at the Q&A asked, what about UL? And I think what they mean is UL does specify gauge thicknesses. They call it MSG. And if you look in the UL guide info, they give the thickness. The minimum thickness for what UL calls 20 gauge is 0.0179, I think. And anyway, or that might be the 25. But
that'd be the 25 gauge,
yeah, the 25. Excuse me. But that's probably what you're looking at. One of the issues is there is no maximum in AISI. So but typically because of the price of steel, they're going to stay pretty close to that minimum.
Yeah. I see Neil Shaw has a hand raised, and
Ryan
as well.
Mine's super quick.
Okay, go ahead, jump in, Ryan.
Hey, I just want to, I had to take a call in the middle of this. It's a really great presentation, and you guys put on lots of great presentations. Really love it. Just want to double check, will there be a link sent out? I see the meetings being recorded. Will there be a link sent out to be able to review this again?
Yeah, there will be a link, and we'll have it posted on our website. I'm not sure if PABCO will post it on theirs. I think in the past they've also posted ones that Ben and I have done. Yeah.
Yeah.
So yeah, we'll send out a link, and yeah, you can check PAC's website where we have our webinars, or check PABCO's as well. We'll have it up there.
Awesome, thanks.
Yeah, Neil.
Yeah, really great presentation. Thank you so much. A couple things. A lot of times, I prepare a detail. The architect takes it. The contractor takes it. Anyone here bake or barbecue? We can give you the recipe, but your results will change depending on the contractor, the whether they're working double shifts and things like that. So, take the lab tests with a little more than a grain of salt sometimes, and be prepared that your mileage may vary.
Yes, very, very much so. And there's a lot of details, and that's the point of sort of presenting this, is like, here are all of these details, and here are all of these things that can affect it. You got to pay attention to them, and look for ways to try and minimize their effects. But they can also be handy tools, right? Like, if you understand what, stud mill thickness and spacing and all of that does at these different frequencies, you can maybe use that to kind of sort of tune your wall to do better at low frequencies or mid or high frequencies or something like that. But yeah, we're sort of painting in broad strokes. I would not, be paying attention to like, oh, I can get an extra 2 dB out of this, because that's not necessarily meaningful within the lab because of test variability, like Norrell said. And then, yeah, you're not going to necessarily see that in the field either, like Neil said. So, broad strokes, but know that there's a lot of variability to pay attention to. So let's see. I know Steve left, and Mike, have you seen anything else? I see questions about certificates of attendance. So we can, this is not like a officially accredited webinar through AIA or anything else like that. But if anyone is interested, I think probably email, what should we have them email, Mike? info@PAC-INTL?
Yeah, that works.
So if you're interested in a certificate, if you would email info@pac-intl.com, then we can get you a certificate of completion. We have those that we do for our webinars typically.
Mike, I got a question.
Yeah.
The early 25 gauge studs, the original high performance acoustical performance studs, not only were the lighter gauge steel, but they were also made springy, such that the flanges sprung out, and you had to compress them back when you installed the gypsum. What's happening today? These newer studs that are equivalents and so forth, do they have that spring in them, or are they just molded and formed to the shape that you just attach the gypsum and it's flat.
I'm going to defer to Dawn, and I think
Yeah,
Elza was also on here too. But yeah, Dawn, take it away.
So I'll take that one on what they're supposed to be. When you manufacture these things, they're supposed to be at 90 degrees. So that it's not supposed to have what they call flare. They do allow some tolerance for flare, but most of the time for studs that thin, flare is not a problem. It's when you get to the 97, 118 mil, that really thick stuff, that it's really hard for these machines to bend them. But for these EQ studs and the drywall studs, they're typically going to be 90 degrees.
Okay. As I remember, I've heard the story that Paul Vennerklausen was involved in the early 25 gauge stud development and so forth, and that there was an intentional flare, that intentionally they were made to flare outward some and to provide some springiness there, which is not present in heavier gauge studs.
And that probably was before my time, because I didn't start in the industry until 1990, and they were trying to make them square back then too. Weren't always successful, but that was the effort.
Okay.
Yeah, so this is a thing that Don had sent me for E90 and for the E1289 reference specimen, as we're trying to define tolerances and things like that. So here's the tolerances. So for non-structural, the flare is plus or minus a 16th, basically, and this is the flare that he's talking about.
Right.
So that's what the specification is now.
Which, by the way, ASI just announced that they weren't going to, they're stopping with their standards, by the way. I don't know what that's about, but I think they announced they're not doing standards anymore. They're gonna not, anyway. Yeah.
Oh man, you had to drop that bomb here, but it is true. The American Iron and Steel Institute is as of December 31st of this year no longer going to develop standards. The good news is the standards they've developed have been adopted into the 2024 International Building Code that I think the online version is already out there. And there have already been multiple meetings by steel industry standards development organizations, and my group AWCI is involved. And it is going to land in a good place. I think the short term is that one of the SDOs that is a part of the steel industry code form, it's called, is going to temporarily house the standards until new SDOs are going to be developed. Right now, it looks like either the SFIA, the Steel Framing Industry Association, or a similar association that is already engaged, is going to be picking up the standards that you just showed on the screen.
Okay.
But more news to come. But we're good probably for the next 3 years or so until a new building code comes out.
Okay. All right.
And Ben, I want to tell you this, that there is another internationally known steel stud expert that runs the engineering department at Johns Hopkins University, who's also named Ben Shafer. So be careful. There may be some confusion. And of course, Shafer is spelled differently.
Yeah, of course. Yeah.
I remember that, Don, when I first started talking to you about Ben. I was like, "Do you know Ben Shafer?" And you're like, "Oh yeah, I know Ben Shafer." And I'm like, "Oh really?" It
it's a
turns out it was a
buddy of mine.
different
Great
Ben
guy.
Shafer.
That's funny.
So in the chat, I have the link to PAC's assembly selector. Somebody had asked for that, for a link to the resources, and also the email info@pac-intl if you want for certificates. And then Ben, if you, or I know there's a number of other PABCO folks, if somebody from PABCO could put in the chat the link to the sound design guide and your resources, so folks can go find those.
I might have to do that. I think because I just came from a industry meeting that we were doing that most people are occupied with. Let me just.
Okay, I see Alan was on here, and I thought I saw.
Oh yeah,
Andy
Alan was
point,
on here.
so.
Yeah. So. Okay.
So Zachary at McKay Conan Hoover asked, Ben, have you published 1/3 octave band data for these tests?
Yeah. Yeah. Go for it, Mike.
And you do on your you have an assembly selector and you have your own reports on there, right?
No, yeah, and then somebody asked. I'll tell you. I'm not even joking. Every single week, I go to my my boss, and I'm like, we need a database. Where's our database? You know, like we've been talking about it for a long time. So I'm gonna keep putting on pressure to get a database where you can kind of mess around with stuff and look at different things. So we're headed in that direction, but we're not there yet. So if you need a test report, you know, you go into the sound design guide and under the where, and you're like, oh, I need this and this test report, and then you can, you know, email or call in or whatever to our people, and then we'll get you the test report. That's kind of how it works right now, which is not great in my opinion, but like that's what we're doing right now. So yes, I've sent like compressed file folders full of test reports to acoustical consultants and people who need like, you know, different, you know, you did a shear study recently. Can I get the test from that or whatever? So I'll like pull that stuff together and send those to you. But like, yeah, that's kind of how it's working right now.
Yeah. Ben, I see that there's a question in here that I know you'll appreciate. Considering the changes in studs, how far back in time would you say a lab test is still relevant? Would you still trust a lab test from 2000, 1995?
Oh shit. Well, you had to ask that question.
I didn't ask it.
I know. Okay, there's two different trains of thought here. The Gypsum Association's official cutoff for a lab test is 30 years. The ICC G2 2010 guideline for acoustics that was published by the ICC says 20 years. And I, in terms of my personal, what we do at PABCO, we test about every 10 years. So it depends on how rigorous you are personally.
But aren't there variations not just in the steel studs, but as everybody's been moving to lighter weight gypsum board? Isn't that gonna? Absolutely. Yeah. So there's a lot of variables out there.
Exactly. No, this is why we tend to, we will go back and we'll retest our stuff after 10 years.
Yeah.
But like,
and there have been some changes in the standards, just, you know, reporting and things like that too. A lot of the older reports you don't get nearly as much information about, things like that. And we're going through a lot of changes in the standards right now. I don't, you know, necessarily know that there are changes that will make older tests, you know, irrelevant, but you know, having newer test methods and things like that is also helpful. And, you know, some of the labs have changed over those decades too. And so the results they get now may not be quite the same as what they used to get, because they've increased the volume of their receiving rooms based on new requirements in the standard or things like that. So yeah, it is good to try and update those. And I see that in the chat, Alan from PABCO has posted links to their different resources as well. So make sure you check those out, because they've got good resources, and I use their sound design guide all the time. So there's a lot of good info in there.
Hey, Mike, we've got a hand raised.
Yeah.
Oh, yeah, sure.
Go ahead.
Hello?
Yeah, go ahead.
Yeah, we can hear you, Fernando.
Yeah, this is Fernando. Back in the question about the old studs versus the new studs and the springability, the tolerance has still been maintained, but on the new studs, we've also changed the profile of the flange that may affect it. If you try to get a standard stud, they used to be all flat flange. Now they have ribs and so forth. So that would affect the tolerance. And also the strength of the flange has to do with the yield strength, which also has changed and gone higher on studs too. So all these factors will affect the performance. And so the old data no longer exists, especially if you're using EQ studs.
Mm-hmm.
Yeah.
Thanks,
Fernando.
Yeah, but sometimes that old data can be helpful. Like I worked on a renovation of a hospital here in Portland, and they had these old like black iron steel truss studs and plaster on either side. And I was like, where on earth am I going to find data for that? I went to the California book. There it was. I found a test for it from like 1953 or something. So, having those historical tests can be helpful, but if we're doing modern construction with EQ studs and lightweight gypsum board and all these kinds of things, we need to make sure that we're paying attention to those details and using test data that actually includes that.
And
Right.
Mike, I just want to make sure that you know that the gentleman just asked the question, Fernando Sesma, has been in the industry longer than I have. He has worked for USG. He has worked for ICCES. He currently works for Simco. So he knows what he's talking about. Matter of fact, just this month, he wrote an article for Walls and Ceilings magazine.
Yeah,
I
recognize
recognize the name, but I couldn't remember where he was.
I read that article, Fernando. It was great.
There you go.
Thank you.
So, and Fernando just had shoulder surgery, so hopefully he can make it to ASTM meetings in a few weeks here.
Yeah, I hope so. And speaking of ASTM, I have pulled Don into the acoustics to ASTM E33, so I think you're gonna be there, right, in person, Don?
That's right, in Halloween costume.
Yeah, unfortunately I won't be there to hang out with y'all, but I think it's I think Don's expertise in in the steel studs and all of this kind of thing will be great to have there.
Yeah.
So
But I'm a neophyte in this acoustic stuff, so I'm there to learn, and but happy to help any way I can.
Yeah. Any other questions here? Let's see.
Mike, there was a question about slides being available after this presentation, and that's I guess that's up to Ben. Typically, we don't make the slides available.
I'm okay with that. I presented this at ASA, so it's sort of public information anyway. Those slides. That was like the San Diego ASA presentation.
Yeah. So I will double check with Ben and the other powers that be at PABCO to just make sure that they're okay with us putting up those slides, because it is their test data that's in there. But yeah, if we can, then we'll put it up, and we can put it up on our website in the webinar section. And we will have a video available. And it sounds like PABCO will have it posted on their website as well. Ben, did you do a POMA for this one?
No, but I've been working on I'm working on like a paper actually about this one, but I might just do a POMA as well. Yeah.
Yeah.
I mean, because we're not done yet.
No, I know. Well, I mean, yeah, and hopefully we'll do this test series too with the RISC clips, and and we'll coordinate with you to try and maintain variables and things like that, so that can add to what you've already got.
Yeah.
Anything else, or Mike, anything else you want to add, or anything else you've seen?
No, I'm good. This is the acoustics version, so I'm more on the sales side, so you probably don't need a lot of input from me. And other than we will be conducting testing to help extend this to the RISC line of products early next year. So it's a good new exciting news, and hopefully we can extend the Ben's research a little bit that way.
I'm super excited.
Yeah, I'm excited to do that. I see in the chat Neil Shaw asked about how about some words about IIC.
We have some words about IIC.
Any kind words, Ben? I think IIC is just it's a completely different animal. Like everything we've talked about here is walls, and for IIC, there's a ton of variables that affect that as well. Ben, have you done any testing besides like the steel C-section joist testing that we've done together? Have you done any other testing on like steel, like C-section joists and things like that, floor ceiling assemblies?
No, not extensively. We haven't. Yeah, mostly the stuff with you.
Yeah. Okay. And the stuff that we have, you can those tests are in PAC's Assembly Selector. Those are steel C-section joists that we did for a particular project. It was condos that were built with resilient channel for the ceiling isolation. They were very expensive high-end condos. People moved in and they were unhappy with the level of acoustic isolation. Surprise, surprise. And so we worked with the acoustical consultant, went and did testing at the lab to kind of evaluate some different options. But those are, ultimately high performance assemblies because they have spring isolators. They have the Rizik SI1 Ultra, which is a spring isolator with a Rizik clip on it. So a different sort of thing. And there again, I would think that the springs having that level of acoustic isolation for the drywall would reduce a lot of the effects of the steel C-section joists, as long as they're stiff enough. And that was one of the issues on that project, because originally it was under-designed structurally, and so it was not stiff at all. So,
Mike, the reason I wanted you to mention IIC is you think we have, too many combination permutations with walls. Think about the ceiling.
Well, that's why I don't even want to go there right now, because there's just too much.
Yep.
Yeah. There are a ton of different variables, and PAC has done more testing on ceilings than on walls, and so especially with our RC1 boost and open web trusses especially, but also I-joists, like I've tried to look at resilient channel variations and those kinds of things, and try and do some more detailed testing looking at those different variables. And we've got some other webinars, and I've got some other like ASA presentations and things on that from the past. Yeah. Thanks everybody for joining us. Anything else before we wrap it up?
No, great. Thanks so much, guys. Bye-bye.
Yeah, thank you all for your input.
Thanks for the opportunity.
And thanks, Don, for your insight, and Fernando.
Yeah. Thanks all of you for your input. We'll post up a recording. And Ben, thanks again for letting me use your slides and your data, and for joining for this presentation.
Yeah, no, it was fun. Good chat.
Yeah, man.
Thanks, guys.
Everybody,
Bye-bye.
take care.